slide बंद कर.
What is the title of the current slide? Because it should be the same slide on which I am speaking.
Yes.
And you are saying.
Okay.
Sushil, stop your slide.
What is the title of the current
Learning.
slide? Learning. Fine.
Ma'am, can I share the screen now?
No. Let it be. Okay.
So what is the status now?
It's first slide. Deep concept in deep learning.
That is fine. I am talking about status of the audience.
Acha, status of the audience. Okay. 17, including you, are there. But I think we should start, sir. Eventually, the people will join.
Yeah, because otherwise already this is night time lecture. So.
Yes, sir. We will start. Let me take this opportunity to introduce Dr. Kishore Bhurchundi, sir. Kishore Bhurchundi, sir, did BE and ME in electronics from SDGS IET Nanded in 1990 and 1992. PhD from now known as BNIT in Nagpur in 2002. He has published more than 80 research papers, including 25 SCI index research papers, which includes IEEE transactions too. He has authored a book on advanced microprocessors and peripherals for McGraw-Hill. He got the selected author recognition from McGraw-Hill for selling around 450,000 copies of the book. He has got 5 patents published to his credit, out of which 2 are awarded. He was principal investigator of 3 research projects, including one on face recognition funded by BRNS and a Center of Excellence on Combated System, a hybrid of communication and embedded system at BNIT Nagpur. He is currently a professor at Department of Electronics and Communication Engineering at BNIT Nagpur. He is also coordinating the programs like Vishweshwarya PhD scheme and Gyan at VNIT worth around 16 crores. He is chairing the committee for setting up a Siemens Center of Excellence on Advanced Technology at VNIT worth rupees 188 crores. He is also chairman of the currently under set up Center for AI, Artificial and Machine Intelligence at VNIT worth INR 1 crore. His area of interest includes image processing and computer vision, wavelets, man-machine interface, learning, embedded systems, and Internet of Things. So I welcome you, sir. Over to you, sir.
Thank you, Madam Ujwala.
Ji.
So as I already conveyed in the abstract of the talk, we'll be starting with the concepts of learning. So as again I had introduced that most of the times students, they are using deep learning, and they are using only just a minute. Just a minute, I'm coming back. There is one. Okay, fine. Okay, so without understanding it is being used, and the basic concept and basic fundamentals of deep learning, even the building blocks are unknown to the students. They are using only MATLAB like toolboxes, and they are doing it. So the intention of this lecture is to introduce to the basic concept and basic nitty-gritties of deep learning to the audience. So I have organized my talk like this. In fact, whatever talk I am giving, it is abstract of around 10 to 12 hours talk. We are actually developing a course on deep learning in terms of slides and PowerPoint presentations. So today's talk is abstract of around 10 to 12 hours talk, because in such kind of talks it is not possible to deal in detail each and everything. But anyway, the concepts can be very rightly presented. So you can see here organization of the talk. I am first introducing uh, the classifiers. Okay, it is indicated by all black titles.
Sir, sorry to interrupt you. Can you
Hello.
repeat the process, please? Stop sharing and again share the window.
Why it has stopped?
Because I resumed that my PPT for your introduction and welcome slide. So it is not visible to all.
It is not visible now.
Yes.
So that is the problem with
Sir,
So
do
I will
stop
have to end the
sharing
show
and
again.
repeat the process. Do stop sharing.
I will have to stop sharing now.
Yes. First and then
Just a minute. How do I stop sharing?
there in present also in present itself that option is there.
In
In present.
Acha, in present itself, this
Hmm. Stop sharing.
resume, resume your presentation. It is showing me resume your
Resume.
presentation.
You can resume also, no issue. Resume
Resume,
your presentation.
resume
That option is
presentation.
also. Now, okay, sir. Now you go ahead. Open the presentation. Yes, sir. Now it is.
Now it is visible.
Yeah.
Okay. So the talk is organized mainly in three logical entities. The first is related to, uh, learning and classifier. Then this white block, SVM, perceptron, and comparison with other classifiers, I'll be dropping from this presentation. However, gradient descent, I will cursorily visit. And then the actual yellow slides, they are related to deep learning. The intention of taking basic classifier here is that every deep learning network in the output stage, it requires a classifier fine, in some form. And that's why a classifier is uh, unavoidable part of deep learning networks. Otherwise also, as we already know, whenever we study anything, whether it is neural network or whether it is fuzzy logic or whatsoever, rough set theory or fuzzy set theory whatsoever, uh, always we study classifier. The reason is that our real life is full of classifiers. Throughout the day we are identifying the objects, that is nothing but classification. We are identifying or recognizing people, that is again classifier. We are identifying currency notes. We are also taking decision whether this is right or this is wrong. So right or wrong or true or false is also a binary classifier. So this way whole life is filled with classifier. So whenever we study artificial intelligence or machine intelligence, we usually talk of classifiers, and that's why as the first block we'll be studying classifier. Then in classifier we have one example, we take perceptron. So this SVM classifier we will drop, but perceptron we will consider, and that is nothing but non-linear classifier, multi-class classifier, and so on. And then followed by gradient descent, and after that we will study the and discuss the concepts of deep learning. So when I talk about classifier, the basic concept of classifier is very important. And when we start about classifier, we talk about binary classifier, means two class classifier. Binary means it can be actually described in terms of 0 and 1. But when we talk about 0 and 1, there are issues. When we implement the things, when we try to implement training of the network, there are training issues. It stretches the same node to logical 0 as well as logical 1. So what we do is, instead of 0 and 1, we consider 1 and -1. Fine, so that the training becomes faster, training becomes easier. So that is a binary classifier. And after that we move on to multi-class classifier and so on, and then to application of that classifier to deep learning. So we basically start from learning. So what is learning? We say that I am learning this, I am learning that. So what do you mean by that? Reading a book or reading set of notes and then remembering the things, it is not learning. Okay, that is comparable to something like overfitting. You might have heard the term overfitting, isn't it? So you have learned something by heart or mugged it up. If the same question comes in your examination, you will get 100% marks. If different question comes, you will get 0 marks. So that is what is comparable to overfitting. So learning is abstraction and application of knowledge. So whatever you have studied, whatever you have learned, you should be able to earn knowledge out of that, and you should be able to abstract the knowledge at different levels. You should be able to abstract the knowledge at different levels. For example, if you have studied a book of 1000 pages, out of that all 1000 pages may not be useful for you, but might be for your course 300 400 pages may be enough. So you should be able to select appropriate 300 400 pages. Then might be that in your 30-40 lectures series, all 400 pages you may not be able to cover, a teacher may not be able to cover. So based on his knowledge, he will select another 100 200 300 pages. Out of those 400 pages, again student will prepare their own notes, might be of 200 to 150 pages. Then finally, suppose you give that book to some expert, he may be able to write 1 or 2 page expert abstract. At the end of the book, on the last page, you will find forward by somebody, okay, or abstraction by somebody. So that is nothing but very very brief abstract of the whole book. So that is abstraction. So abstraction is very very important for knowledge. If you try to mug it up, then it is not learning. Knowledge is represented by information, isn't it? You do not get knowledge ready made in the market. What you have to do is you have to read books, and books contain information. Books do not contain knowledge. This is very important statement. Books will contain information, and when you study the books, okay, you will have to extract knowledge. So what does it mean? All information may not be knowledge. Okay, then information in the books, it is represented by data. Data may be available in the form of text or labels. Then it might be available in the form of numbers, or it might be available in the form of mixed data also. For example, many of us are teachers. So we have, for a particular subject, we have names of the students. Those are available in terms of labels. Then might be marks earned in T1, test 1, test 2, and same. So there are marks also. So names of the students are there, marks are there. Okay, so marks are in terms of numbers, then names of there in terms of labels. There might be mixed data also. For example, you have registration number of the student. So you may have something like BT, then 2002, that is batch of admission. Then might be branch, say ECE, and after that might be roll number 010. Okay, so this is mixed data now, which contains characters also, which contains labels also. So there might be labels, there might be numbers, there might be mixed data. Then abstraction involves acquisition, analysis, estimation, trend evaluations, and so on. When I talk about abstraction, what does it exactly contain? First thing it contains is acquisition. Means if I have got a book, I will have to read it. If I want to have marks of a particular class for a particular subject, I will have to first evaluate the answer sheets and enter their marks into that Excel sheet. That is the process of acquisition. Then there is analysis. If I have got marks, I will have to find out what is the percentage of result. Okay, whether the result is less as compared to the last year, or it is more as compared to the last year. In which questions students have got more marks. All of you are doing NBA, so you might be computing your CO PO attainments and so on. So you might be you might be carrying out analysis whether the students have got more marks in theory questions or more marks in problems. Okay, and most of the times we know that students get more marks in theory questions because they tend to mug up the things, so they get a lot of marks. But when it comes to solving problems, they get less marks. So this is what is analysis. Okay, then there might be estimations. What is the percentage of result? Okay, then there can be trend evaluation. whether the results have increased, they have decreased, a particular subject has got more percentage of result, a particular subject has got less percentage of result, and so on. Okay, these are all trend evaluations. Then there can be trend analysis. If there is a rise, then by what percentage the result has improved? If there is fall, by what percentage the result has fallen? This is what is trend analysis. There can be pattern analysis also. So what I talked so far, it was about numerical analysis, but there can be pattern analysis also. What are the examples of pattern analysis? I can have a pattern like say a facial photograph of somebody, and then I want to identify who is the person in the picture, okay, or who is the person in the photograph, whether he is my friend or he is my brother, sister, mother, father, and so on. I can recognize a person. Not only recognizing the person, I can even analyze the pattern, that the photograph has come good or the photograph is dull, the colors are good. This is what is the physical observation based analysis. There can be even contextual analysis. The person is sad, the person is happy. Expression analysis. From the facial photograph, I can make an expression analysis. Then there might be a currency note. I am able to identify whether it is 100 rupees currency note or whether it is 2000 rupees currency note. Then in that I can also identify whether it is old design note or whether it is new design note, whether the note currency note is new brand or the currency note is old, and so on. Then there can be detection. A photograph can be given to you, and in that photograph you can detect a vehicle, you can detect a motorcycle, you can detect a car, and so on. You can even match the patterns, isn't it? When you identify that this is 2000 rupees currency note, you are matching the pattern with standard currency note of 2000 rupees. Then there is recognition. Recognition can be anything. I mean, matching is one way of recognition. Suppose there is some song playing on, you can identify the song and you can take a decision that this particular song in from this is from this movie. Okay, so you are recognizing the things. Then there is analysis. Analysis means what? Further analysis of the signal. There is a song, but there is a lot of noise, and even in presence of noise you can recognize the song. Okay, so all these things, they are examples of pattern analysis. Pattern might be two dimensional like picture or currency note. Pattern even can be three dimensional like video. Fine. Then there can be detection based on that pattern. There can be one dimensional pattern like speech signal, song, and so on. There can be biomedical signals like say ECG signal, that is one dimensional signal. There can be fMRI signal, functional magnetic resonance imaging. So you can have three dimensional signal also. You also can synthesize the signals. Means what? You listen to a music, you listen to a song, and you try to sing the song. Means you are trying to replicate the song. That is what is synthesis of the signal. You see photograph of a movie star, and that you try to reproduce, you try to paint a picture of that movie star. So that is again pattern synthesis. So these are all outputs of learning. Fine. Then, and applications of learning also. Then application of learned knowledge to real life problem is the final outcome of the learning process, whether it is human learning or machine learning. If somebody is saying that I have completed my BTech or MTech or PhD, and if he is unable to solve real life problem of different complexities, then that learning is not learning. Whether it is human learning or machine learning, when you say that machine has learned, it should be able to solve the real life problem for which it has been trained, or whatever it has learned. The same thing is applicable to human learning also. Both of these, they involve forced and repetitive input of data oblique efforts. Whether it is human learning or machine learning, both of them, they involve forced and repetitive input of data and efforts, then correction of data and efforts, input and closed loop output check and correction. Now this particular last statement which I have shown in, I mean, red font, this is very, very meaningful. Try to remember how we learned in our childhood when we were in KG1, KG2, or first standard, whatsoever. So our teacher has taught us 100 times that this is 1 and this is 2 and this is 3, this is A and this is B, so on. So that input was forced input. Forced input means what? There is no provision of asking why this is 1 and why this is 2. This is 1 and this is 2, that's all. That's why the input was forced upon us. Okay, and many times, in what ways our teachers and parents, they have forced learning on us by naturally or by liking. Very few children will like to learn. Most of them, they are forced to learn. Now when we talk about forced learning, there is repetitive input of data. Our teacher might have taught us, or father mother might have taught us 100 times that this is A and this is B, so it is repetitive input of data. We have taken this efforts repetitively for many days and many months to learn the basic things like ABCD and 1 2 3 4. Then correction of data and effort are there. Many times a child, he writes wrong thing. Specifically, there is confusion between, say, small case B and D, small case P and Q, and so on. So the child write it in a wrong way. They are mistaken for each other. So the teacher corrects the data. Okay. Many times we appear for the examination and we do not get marks. Then we go to our teachers and tell the teacher that, teacher, I have studied very hard, but then I didn't get marks. Then your teacher tells you that whatever you have studied it in a wrong way. Your efforts were in wrong direction, so you have to correct your efforts. So correction of efforts are required. Fine. We use different algorithms for training of neural networks. If normal gradient descent is not enough, we apply gradient descent with momentum. So that is what is correction of efforts. Fine. Correction of data, a particular data set may not give you good results. So you take more complex, more challenging data set. So correction of data is there. Inputs are also corrected, means data set is corrected. Then this is very important. Closed loop output check and correction system is there. We study for something, we appear in the examination. Say for example, GATE examination, you get 90%, 90 percentile, and then you come to know that with 90 percentile you are not going to get any good institution. So what you do is you prepare again. Okay, so whatever was your mistake or error, you, for correcting that, you are studying again. So it is a closed loop system. You have put in your effort, you have evaluated yourself through some examination, your percentage of marks was less, you are again studying and again appearing. Just like that, even in case of neural network, you apply an input pattern, you calculate the error at the output, you already know the target output. What is your target? So target minus actual output, you get the error. If that error is not acceptable, you again apply the new pattern, change the weights. Okay, you correct the weights, again calculate the output, again check the error, and this process is an iterative or repetitive process. So that is what is closed loop output check and correction. So note that this process of closed loop output check and correction, it is not only for machine learning or artificial intelligence, it is also applicable to human learning. So with this much introduction to learning, we now move on to the concepts of machine learning. In machine learning, information takes shape of numerical data. Okay, because we implement machine learning using what? Using digital computers. And as you already know, digital computers only understand numbers. Note that digital computer only understand numbers. Even if there are labels, there are characters like ABCD inside the digital computer, they are represented in the form of their ASCII codes. You already know this. Even if you implement fuzzy set theory program, there are something called as membership functions. All the calculations are done on membership functions. So digital machines, they only work on numbers, and numbers are also represented using different formats. As you already know, you talk about 8-bit integers, you talk about 16-bit integers, then 32-bit integers, and so on. You talk about floating point formats, then 32-bit floating point format, 64-bit floating point formats, when it comes to graphics processors, you may have even 128-bit floating point formats and so on for graphics calculations. The gist of the story is the digital machines, they only understand numbers. So whatever is the information available, you will have to express it in the form of numbers. Fine. So the conventionally the numerical data was pre-processed. Now when I talk about pre-processing of data, what is it? What may happen is, whatever data many times you get, it contains noise, it contains unnecessary data. So you will have to take appropriate decision. You will have to identify right data and wrong data. There might be algorithms for that. You call it pre-processing algorithms. You might have heard about filtering. In case of digital image processing, there is something called as median filtering, which avoids salt and pepper data. Then salt and pepper noise. Then there can be Gaussian noise for avoiding or minimizing Gaussian noise. There are averaging or mean filters and so on. So there are pre-processing techniques. Pre-processing techniques avoid unnecessary data. There are many times outliers. Those who have studied probability and statistics, they might be knowing about outliers. So those outliers are dropped from the training data, because otherwise they will create problems in training of the network and so on. So pre-processing is required. That is also called as pruning of the data or thinning of the data. It is quite possible that many times same number or same reading might be repeated n number of times. So you may not require same reading n number of times. Only one set of input and corresponding to that one set of output is enough. So that data needs to be pruned or thinned, and then it is applied to the learning system like neural networks. Otherwise, if your data is not properly organized, this is what is also called as data cleaning. In data sciences, you might have heard the term of data cleaning. So that is nothing new. If your data or if your signal is having some noise, you will have to avoid that noise, you will have to minimize that noise, and then only your data will become useful, it will become applicable to systems like neural networks. And that's why pre-processing of the data is very, very important. And as I already told you, a few of you might be computer science people, so in data science you might have already come across the term data cleaning. So that is nothing but pre-processing. We electronics engineers in signal processing, we call it pre-processing. In data science, you call it, uh, I mean, uh, data cleaning. Okay, or some probability person may call it removing the outliers. Fine. Then it has been observed that most of the real life applications are modeled as classifiers. I have already told this to you right from morning. As soon as we wake up, uh, our eye opens, we will try to take a decision whether it is still early morning, very early morning to wake up, or it is already morning and sun has come up. So this is again a classifier, whether you should wake up or you need not wake up. This is again a classifier. After you wake up, you try to locate your uh, hope all of you and including me try to locate our toothbrush, isn't it? So whether the object in front of your eyes is a toothbrush or it is not a toothbrush, it is again a classifier. Then somebody may try to locate a comb before toothbrush. So whether it is a comb or whether it is a toothbrush or whether it is whatsoever, that is again a classifier. You are identifying an object. Hence, classifiers are the most frequently observed entities in machine learning. It is mostly required in real life. That's why we mostly study it in machine learning, neural networks, fuzzy set theory, rough set theory, everywhere. Wherever you go, classifier is there. Now, most of the work in machine learning evolves around designing a classifier, which can be used for specific real life applications very robustly and accurately. Those who have carried out their projects in neural networks or fuzzy set theory, and they have trained a classifier, at the output you find out its accuracy, you find out its specificity, and so on, repeatability and so on. So you call it something like confusion matrix. Okay, so that is the process of working out efficiency of your classifier. Now the target is you should have 100% accuracy, 0% misclassifications, and so on, 100% repeatability. Okay, but a practical classifier doesn't satisfy all these ideal requirements. Okay, so the classifier which will carry out all these satisfy all these requirements, it may be considered as an intelligent classifier. But then in fact intelligent, the word intelligent, it has got many uh, perspectives. It is not only based on the numerical result. Many times it is context based, many times it is situation based, and so on. Many times it is person based also. So that's why is something called intelligent decisions. Okay, so as far as the current lecture is concerned, we will try to stick to intelligence of the classifiers, or what we call computational intelligence. Fine. Now this sentence is very important in the context that a classifier which is trained for a specific real life application is expected to perform only for that application. For example, you train a classifier for recognizing faces, human faces, and if you use the same classifier for recognizing, say, a currency note, it will badly fail. Or vice versa. If you train a classifier for recognizing currency note, and if you try to use it for facial recognition, it will badly fail. Okay. Not only that, if you try to train a classifier for recognizing a dollar, and using the same classifier, if you try to recognize some Malaysian currency, it may badly fail. Okay, so in general, machine classifiers, though they are considered intelligent to some extent, they may badly fail in other applications for which they are not trained. On the other hand, they may work very accurately for the applications for which they are trained. In fact, in real life, a classifier or algorithm, there is no algorithm which is intelligent at absolute level like human brain, and that's why human brain is still considered, even human brain of a most average person, or you may call it some even uneducated person, okay, who has not been trained, but he will be very good in real life applications. Fine. So a classifier or an algorithm is as intelligent as the mathematical formulation behind it, and no classifier is brilliant at absolute level like individual humans. Okay, even humans, are they trained for large number of real life applications? I will say no, because if a person is a doctor and if he is asked to solve a computer science problem, he will badly fail, or vice versa. On the other hand, a computer science engineer, if he is asked to diagnose a particular patient, he will badly fail, obviously, isn't it? Because a doctor is trained as a doctor, or a computer science or computer engineer is trained as a computer engineer. They are not trained for each other's job. Fine. So, so uh, you will have to train a classifier for every application. Is the screen visible to you?
Yes, sir.
Has it changed the slide?
Yes, sir.
So the current slide is concept of learning, a linear classifier.
Yes.
Fine. Okay. So I will have to keep on checking this, because my experience is that, uh, I mean, in between also many times it stops working. So anyway, however, there are some brilliant people like Pascal. You might have studied work of Pascal in chemistry also. You might have studied work of Pascal in physics also. Okay. In physics also, he has worked in many areas, right from pressure theorem of Pascal you might have studied in your early school days. Okay, he has worked in thermodynamics also. Then Dr. J.C. Bose, as you already know, he has proven that plants can breathe, and he is also considered as a father of wireless communication. So there are some people who can work in multiple fields, but even J.C. Bose and Pascal, they also were not effective in very large number of fields. Might be 2, 3, 4, 5 fields they were effective. but then many fields they were not working also. So further we try to understand the concept of a basic classifier, starting from very basic to deep learning. Now, when you start learning classifier, the first term you come across is a linear classifier. So here we first see what is a linear classifier, and for explaining the concept of a linear classifier, we will take example of a two-class classifier. Why it is called a linear classifier? For that, for explaining that, I will go to your fifth standard knowledge of mathematics. We already know y is equal to mx plus c is equation of line. Okay, and this contains infinitely many points, x and y, combinations of x and y, couplets of x and y. But you know, as soon as I write equation of the line, what I have achieved when I write equation of line, what I have achieved, note that infinitely many points xy, they have been represented by only two values m and c, and xy they are the input to the equation. Okay, given any value of x and y and given the corresponding values of m and c, you will be able to judge whether the point xy lies on the line or it doesn't lie on the line. The process is very simple. You substitute x and y in the equation y is equal to mx plus c. The equation is satisfied, then you say that the point is on the equation, otherwise you say that it is not on the equation. Note that the above equation y is equal to mx plus c, which you have studied in the fifth standard, it has abstracted infinitely many points into only two parameters m and c. So this is the first example, very first example of abstraction, or this is very first example of even, what should I say, data coding. Infinitely many points x and y, they have been coded using only two values m and c if they are lying on the equation or on the line represented by equation y is equal to mx plus c. So this is huge level of abstraction. Okay, or in terms of signal processing we call it coding also. We have coded infinitely many points using only two parameters m and c. The equation of the line I can write like this also, y minus mx is equal to c. Now this particular equation expresses c as a linear combination of x and y. Those who have studied linear algebra, they may, or otherwise also, this is very basic knowledge, linear combination of x and y. There is one parameter or one, what do you call it, coefficient of y, multiplier of y. In this equation, say it is 1. Then another parameter m is multiplier with x, and third value c is a constant. In this equation, c is expressed as linear combination of x and y. Okay, with coefficients 1 and m. 1 is multiplier of y or coefficient of y, and minus m is coefficient of x. This is called as linear algebraic point of view of the same equation, y is equal to mx plus c, nothing new. The same equation of line also can be written as y minus mx minus c is equal to 0. And you will be surprised that this works, this particular equation y minus mx minus c is equal to 0, it works as a two-class classifier. Fine. And it has originated from the basic equation of line. That's why we call it as linear classifier. How does it work as a classifier? Note that in this equation y minus mx minus c, m and c are given constants, and suppose one point xy is given to you, you substitute xy in that equation, and if you are getting y minus mx minus c is equal to 0, all these points for which you satisfy the equation y minus mx minus c is equal to 0, they are considered to lie on the line itself, and this line is nothing but boundary of the two classes. What are those two classes? What are those two classes given in point 2? For all the points x comma y, for which y minus mx minus c, if it is greater than 0, the described class is a set of points in the x comma y space or xy space that lies above the line. Then Next class, that is for all the points x, y, y minus mx minus c less than 0, the represented class is a set of points in the xy space that lies below the line. Fine. So what has the line done? The line has divided the xy space in three regions. What are those three regions? First region is the space above the line. The second region is the space below the line. So it has divided the xy space, complete xy space in two regions, above the line and below the line. That's why the line is a two-class classifier.
Mhm.
And the line itself is the boundary of the two classes.
Yes.
The line itself is the boundary of two classes, and that's why we call it linear classifier.
Mhm.
Means the two classes, that is above the line and below the line,
Mhm.
okay, they are separated by this line. The boundary is taking the shape of the line. That's why we call it a linear classifier. Okay, now thus the line works as a classifier to classify the complete xy space into two sets of data points, above the line, below the line, and so on. So I won't be reading, I mean, each and every line in the uh, presentation, because I want to save time also, but I am explaining most of the things, so there won't be any issue in understanding. So starting from this particular point, this is a concept of basic classifier. Now the issue is how to convert this into a computer algorithm, or how to convert it into hardware. Let me tell you that we can convert all these algorithms like gradient descent and all that into corresponding uh, analog circuits or digital circuits also, circuits implemented by hardware. And you might have already heard that there are neural network chips available. Okay, so these are nothing but hardware replication of the software algorithms like gradient descent. So now this particular linear classifier, from this particular equation of line, we move on by using some simple mathematical treatment to evolve the architecture of a basic neural network. So as we have already seen, x1 y1, if I consider one point as a feature of a point, say x comma y in xy space, okay, rather than now calling it coordinates, now I am calling it feature of a point A in xy space. So x and y space, it has got two dimensions, and every point is now an object in xy space. Similarly, x2 y2 will now be a point or features of the point in xy space. So I am considering x1 y1 as say point A, x2 y2 as point B, and so on. You can consider third point also. But as far as line is concerned, as you already know, there are only two points required for describing a line. Now suppose I consider an example. When I am considering this x1 y1 x2 y2, how do I transform this particular xy space into a real life application? There can be a three-dimensional space also. Instead of x and y, I can have x and y and z. Okay, there can be a space, imaginary space, which can be four-dimensional space. Fine, there can be x, y, z, and again fourth coordinate m, and so on. Okay, so now to elaborate this, I will move on to another presentation, and I will try to, how do I go back? I will have to end the show for that.
Yes, sir. Sushil, please guide.
Doesn't matter. Yeah, I have done it. So I will now open another presentation. Uh, okay. So how do I take this new window? I am not very. We are in habit of Webex.
And that presentation visible to us. Kindly open that presentation.
Just I open. It will be visible to you.
Yes, yes. Yeah, visible to us.
Okay. I have opened this now.
Yes, yes. It is visible to us.
Visible.
Just
Yeah.
F5.
Is this
F5.
an example?
Yes, yes,
Okay.
Visible.
yes, yes,
So I am taking
yes.
an example now, just for the understanding of, for the sake of understanding of those who have not studied application implementation in neural networks. Suppose I have got 10 students named A, B, C, D, E. These first five, they are male students, and the next five, F, G, H, I, J, they are female students, suppose. Fine. And I want to identify them on the basis of their parameters. So for example, height is the first parameter. So A has got 5.8 height, B has got 5.9 height, C has got 5.10, and so on. Girl F has got height 5.5. Then accordingly, girl H has got height 5.1, and so on. So first parameter height, I can consider as a X parameter. Next parameter is weight. A boy has got, A has got weight of 85, boy B has got weight of 90, and so on. Boy E has got a weight of 55. He appears to be very thin. And then girl F, she has got weight 50 kgs. Girl H has got 45. Girl J is having solid personality, so her weight is 88 kilograms. Then accordingly, third parameter is suppose there Z, that is 7.5 IQ. IQ is being described on the scale of 10, and so on. So A has got IQ of 7.5, girl J has got IQ, accordingly has got IQ of 7.2. Now I am trying to represent them in XY spaces. So see the first XY space diagram. On Y axis, I have got H, that is height of all students. On X axis, I have got names of different students, A, B, C, D, E, F, G, H. Okay. Now I have marked heights. A has got height 5.8. Note that the diagrams are approximate. They are not very exact. They are all hand-drawn diagrams, not Excel generated. A has got 5.8 height. Accordingly, boy E has got height of 6 feet. Then girl F has got height of 5.5, and the last girl J has got height of 5.7. Now in this diagram, I want to identify or classify boys and girls. So what can be my one option? One option is the red vertical dotted line. See here, between E and F, I have got dotted line, vertical red dotted line. So what that dotted line is describing? That dotted line is dividing this space in two parts. On left hand side, all boys are there. On right hand side, all girls are there. Fine. But note that this red dotted line is not the only option. I can have yellow dotted line also. Now all boys, they are above yellow dotted line, and all girls are below the yellow dotted lines. So what this is doing, what these lines are doing, they are dividing the space in two portions or two classes, boys and girls. Fine. In the second figure, figure 2, for the time being, I am not considering height, I am considering only weight. Weight is from minimum weight is 45, maximum weight is, I am assuming, say scale 100. And now I have plotted weights of boys and girls against their names, A, B, C, D, E, F, G, H, I, J. Okay. Now in case of the second weight space, weight and namespace, what you observe is above pink line, you will find all boys, and below pink line, you will find all girls. So what this pink line is doing? Again, it is dividing this space, weight and namespace. Now on axis, we have names of the boys and girls, A, B, C, D up to IJ. So this space, this pink line is again dividing into classes. Now what I do is, I drop these names. A, B, C, D, H, I, J. I drop these names, and I consider this space now. On x-axis, I take weights. On y-axis, I take height. Okay. Now see what will happen. What has happened? every point in the weight height space, instead of xy space, I am calling it weight height space. Every point in the weight height space now is a person. See here, the person H has got height of 5.1 and she has got weight of 45. Okay. Similarly, boy D, the last point in the space, boy D, he has got height 5.5 inches, 5 feet 11 inches and weight of say around 95 or 100 kgs. Fine. Now this has become height and weight space, and every person has become a point in the space. Is it clear? I hope this is clear to everybody. Every
Yes, sir.
whether
Yes,
a
sir.
boy or a girl, they have become a point in the space, two-dimensional space, weight and height. Now suppose if I use third axis for IQ, what will happen? Every person will become a point in three-dimensional space. Now instead of height, weight and IQ, I take 100 parameters. It might be skin color, it might be emotional quotient, okay, it might be, I mean, anything. I can take 100 parameters of an object, 100 features of an object. Okay. In that case, I will require 100 axes to represent every object. Now I am considering here a person as an object, okay, in the space. Fine. So if there are 100 parameters, every person will become an object in 100 dimensional space. And that particular person will be represented by a vector containing 100 feature values. Fine. So the vector representing every person will be called as feature vector. And this 100 dimensional space will be considered as feature space. Instead of 3D, it can be 100 dimensional, it can be n dimensional. I hope this has cleared your concept about feature spaces. Now I will close this down, and I will go back to my original presentation, or let it be on. Is this new thing visible to you?
Yeah. It is concept of learning a linear classes.
Yes. Thanks for cross verification. Now the same equation of line, directly you go to the last but one bullet. I have described all these points by giving the example. Last but one bullet. Equation of a line in 2D xy space is y is equal to mx plus c or y minus mx is equal to c. Now here I am dividing this by c. So what I will get? Y by c minus x by c is equal to 1. This represents a class that is above the line. Fine. And obviously, y by c minus x by c is equal to minus 1. Okay. If it is 0, then it will be a boundary. Okay. Or minus 1 equal to 0, it will be a border line of the two classes. But if I consider y by c minus x by c is equal to minus 1, this will represent class 2. Okay. So y by c minus x by c is equal to 1. This will represent class 1. And y by c minus x by c is equal to minus 1. It will represent class 2. And how they have been derived? They have been derived from the basic equation of line y minus mx is equal to c by dividing by c. Fine. I can also write this equation as ax plus by plus c for a linear boundary of two classes. This I have already described. Now see, I have plotted multiple examples here. The straight line, red line, you can see all points above line. I am calling them class 1. The slope of the line is m. And what this line is above, what is the region about the line represented by y minus mx minus c. This is greater than 0. Or y minus mx minus c less than 0. Fine. All the points above the line, they are class 1. All the points below the line, they are class 2. Now, for this greater than 0, I have taken actually 1, and for less than 0, I have taken -1. Okay. This is going to facilitate me some tolerance around the line, +1 and -1, instead of a single line. If I take it is greater than y minus mx greater than 1, means it will represent some tolerance above the line, some tolerance below the line. Okay. Then I am taking second example. In real life, though we keep on studying linear classifier, we start with it and then move on to complex classifier. Most of the times, let me tell you that we try to implement everything using linear classifier. Why? The reason is very simple. The reason is that linear classifier is easier to study, is easier to implement. But real life applications, they may not be always implemented using a two-class classifier by a straight line. The application may be like this. You may require two lines to represent them. Two red lines you are seeing here. One red line, rather than line, I will call it a ray. Okay, with positive slope, another with negative slope, and crossing at a point on x-axis. So inside the two lines, that is class 1 suppose, and outside the two lines there is class 2. Now such kind of classifier you will have to implement by using a curve like this. Might be hyperbola, or might be a parabola. Okay. Then there can be third application. I have shown here a circle. Outside the circle, that is class 1. Inside the circle, there is class 2. Fine. Now, how these classes will be described in this second diagram and third diagram? Suppose the equation of this curve is C. C is equal to 0. Whatever is the equation of the curve, I will express it in the form of this equation. C is equal to 0, where capital C is some mathematical expression equal to 0. You substitute xy points, or it may even have x, y, z, m, and p whatsoever, depending upon the number of features. So after substituting the points x, y, z, m, n, if you get a number equal to 0, it means the point is on the boundary. If it is greater than 0, it is outside the curve. If it is less than 0, it means it is inside the curve. Fine. Like here, outside the curve means you will be clearly able to demarcate it in the third diagram, outside the circle and inside the circle. So equation of the circle is x square plus y square minus r square is equal to 0. Fine. Value of r is known to me, and if I substitute x and y, what will happen? If I get a value equal to 0, it means the point lies on the circle, that is nothing but a boundary. But if it is greater than 0, it will represent class 1, that is outside the circle. If it is less than 0, then it will represent inside the circle, that is class 2. However, let me tell you, we have taken here in the first three diagrams very, simple and convenient examples of classifiers. In case of real lives, you may have large number of classes. There may not be only two classes. In the last diagram, I have shown class 1, class 2, class 4, class 5, class 3, and so on. There are 5 classes shown. There can be large number of classes. Not only that, these classes may not have fixed mathematical equations like this. Like x square plus y square minus r square is equal to 0, or y is equal to mx plus c. Boundaries may not have fixed geometrical equations. Boundaries may be irregular without any mathematical equations. Now, all such classifiers, real life applications, you will have to solve them using classifiers like fuzzy set theoretic classifier, rough set theoretic classifier, neural networks, all complete soft computing techniques. There is a complete class of classifiers. They are called as soft computing classifiers. You will have to solve such problems using such applications. At least in this last diagram, I am showing all these classes separate. They can be separated using some class of boundary. Okay. However, in case of applications like biomedical applications, you will find that even the classes cannot be separated by a most complex classifiers. because what may happen is that 2-3 points of class 4 will enter class 5. They might be at the heart of class 5, or 2-3 points of class 1 might be available at the heart of class 2. 1 or 2 points of class 2 may be at the heart of class 3, and so on. The points may not be even separable. In such cases, it becomes very, very difficult to design a classifier, and the errors in the classifier output, they are large. Fine. However, there are some complex algorithms which have come up, SVM, these, that, and so on, that they can implement most complex applications very accurately. Okay, this I have given, these figures I have given to offer you the idea about complexity of the classifiers, but still I will say that whatever I have shown in this slide, they are still not the very complex classifier. So far we have talked about 2 axes. If there are 3 axes, then what will happen? Ax plus by plus cz is equal to d. This will be equation. Fine. We have all studied 3D geometry in our 12th standard or 11th standard. The equation was like this. Fine. Ax plus by plus cz is equal to d. And we call it equation of a plane. We call it equation of a plane. Similarly, if there are n dimensions, if I consider 100 feature of every person, height, weights, skin complexion, ethnicity, okay, IQ, EQ, okay, large number of parameters of a person, hemoglobin, okay, by all biometric parameters and so on, biological parameters, I may have 100 parameters of each person. I will require 100 axes for that. Fine. If I consider n axis, what will be equation of such plane? Obviously, it will be ax plus by plus cz plus dash 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 plus nn is equal to m. Okay. So this is equation of a plane in n-dimensional space. Note that such spaces where number of parameters are large, they cannot be drawn on 2-dimensional spaces. Neither they can be represented on 3-dimensional diagrams. Okay. So they are all called as more than 3 dimensions. They are all called as hyperspaces. And the equation of the plane ax plus by plus cz plus dash 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 plus nn is equal to m. This equation is called as equation of a hyperplane. Fine. Now I will again divide both the sides by m, just like we divided by c in the last example. I am dividing by m now. So I get ax by m plus by m plus cz by m plus dash 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 plus nn by m is equal to 1. Okay. So if I have a point x, y, z dash 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 n, I can substitute the values a, b, c, n, capital N, they are known constant. Capital M is a known constant. Fine. So if I have a point, I can substitute it in this equation. If I get more than 1, I will call that it is class 1. If I get less than 1, I can call it as class 2. Fine. Or this 1 I can take on left hand side, and nn by m minus 1, if it is greater than 0, I will call it class 1. Less than 0, it will be class 2. Now see here what I am doing. I am taking here A, B, C, D, M, N. What will happen if I have 100 parameters? I have got only 26 A, B, C, D. So instead of having A, B, C, D, I am replacing this constant A by M, B by M, C by N, N by M by coefficients, constant coefficients C1, C2, C3, Cn, and so on. Okay. Assuming n-dimensional space. It is n plus 1 because there will be a constant number. And there will be variables x, y, z, n. Okay. And this x, y, z, n, again I have got only 26 characters. If I have 100 variables, I cannot take x, y, z. I will have to take x1, x2, x3, xn, so that I can take x100, x1 lakh, and so on. So the above equation I can write as, see here, c1 x1 plus c2 x2. This is not x21, this is by mistake x21, it is actually x2, plus C3x3 plus dash 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 Cnxn. Fine. This is equal to 1. This is nothing but linear combination. Okay. Same equation. Can I write like this? We have been doing like this. K is equal to 1 to n. Ck xk is equal to 1. Or I can write k is equal to 1 to n. Ck xk minus 1 is equal to 0. Note that 1 can be anything if you do not normalize by m. Here this 1 is there because I have divided by m. This is called as algebraic notation. I can write the same equation in matrix notation also. How will be the matrix? C1, C2, C3, Cn. Okay, and minus 1. Last coefficient I am keeping minus 1 multiplied by another matrix x1, x2, x3, xn. Last will be 1 and transpose of this. Transpose of this because, as you already know, according to the definition of matrix multiplication, we take row of the first matrix and we take column of the second matrix. So this second matrix x1, x2, x3, xn and 1, if I want to convert it to a column, I will have to take it transpose. And then this is written as capital C multiplied by, that is matrix C multiplied by matrix X transpose is equal to 0. This is called as matrix notation of a classifier, where C is coefficient matrix while X is variable matrix. Fine. Or feature matrix. Capital X is also called as feature matrix. Because feature are varying, we can call it variable matrix also. All represent a two-class linear classifier and all are the same but only different way of writing. Now, what we do is we transform this equation into a basic neural network. How do I do it? Note that this equation k is equal to 1, ck xk is equal to 1. I write, instead of ck, I write wk xk. Because in neural networks, we use the terminology of weights. And weights are nothing but coefficients or multipliers. So k is equal to 1 to n, wk xk is equal to 1. Or I can write it like k is equal to 1 to n, wk xk minus 1 is equal to 0. Fine. Now, this is something like whatever you have studied in even in your control system or any other thing you might have studied in your graph theory also. Graph, this thing, what do you call it? Nodes and path. A path can also have weight. Okay. So the arrows, they are the paths and they have weights w1, w2, wn, dash 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 wn. Inputs will be x1, x2, xn and so on. Okay. So the first nodes, they are only transfer nodes. They take input x1 and pass them as it is they are at the output. Okay. And this path, it will multiply input x1 by weight w1, so that at the input of the summing node, the plus mark node is summing node. At the input of the summing node, it will be w1 x1, accordingly w2 x2 and dash 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 accordingly wn xn. And this minus 1 constant is called as bias. I name it as bias. Okay. So at the output, what I will get? Output O will be equal to w1 x1 plus w2 x2. Now please forgive me for these notations. This 1, 2, they should all have been what do you call it, suffixes, but they are written as full characters. Dash 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 wn xn, and to that summation minus 1 will also be added. So the equation finally will be the required equation. K is equal to 1 to n wk xk minus 1. Fine. So I hope all of you have understand how the small equation of the line which you have studied in your 5th standard has been converted into this diagram, which we call as very basic neural network. Okay. Very basic neural network. Single output perceptron. This is called as single output perceptron. Output is single, but it can represent two classes. The same output, when it is 1, it will represent class 1. When it is minus 1, it will represent class 2. Fine. Now, how to change these weights? Before changing the weights, what I do is, this bias, which was minus 1, I transform it this way. I call it input x0. to simplify the equation, I call bias input as input x0 and I fix its input at -1 by W0. X0 is equal to -1 by W0 and weight of bias path is W0. So that -1 by W0 multiplied by this W0, that is equal to -1. Okay, this is only change style of drawing and no technical change. This is giving me now this equation. Note that in the earlier equation, it was k is equal to 1 to n and -1 was separate. Now that -1 I have, for simplicity, I have combined in this equation. K is equal to 0 to n, wk xk, and w0 x0 represent bias. Okay. Now the issue is, I have got x1, x2, xn, an input pattern, and I already know beforehand the class of the output. For example, I know that a person with weight 90 kg and height 5 feet 11 inches is a boy, and for boy I represent it by +1, suppose. Fine. A boy is represented by class +1 and a girl is represented by class -1. I represent x1, x2 parameters of a boy at the input, and I force this output to +1 by changing the weights w1, w2, wn. Initially, I can assume random values of w1, w2, wn. I can apply the input parameters. I may get some value here. Now that particular value, okay, if it is suppose -0.5, but I know that he is a boy. So what I will do? I will change this w1, w2, wn such that the output from its current value of -0.5, it should move towards +1. So the targeted output is +1. So I can calculate the error between actual output and targeted output. Targeted output is +1. My current output is -0.5. So what is my error? What is my error? Error is equal to O minus O target. Okay. Where for a boy, O target will be +1. For a girl, O target will be -1. Fine. So for O, I can substitute this value. K is equal to 0 to n wk xk minus ot. This gives me error for an ith single input pattern. I am talking here about ith single input pattern because first pattern might be a boy, second pattern might be a girl, and so on. Okay, it is not necessary that whenever you give a data set, all the parameters of boys, they will be given first, and then all the parameters of girls, they will be given at the end. Not necessary. The data is usually mixed data. Okay, for appropriate training, we randomize the data. It is called as randomizing the data. So first parameter might be first person might be a boy, second might be girl, again there might be girl, third person might be boy, and so on. It might be a mixed data, as I already said. So this is what is my error. O minus OT, where I have substituted value of O from this particular diagram, k is equal to 0 to n. Then I define a term that is squared error. Why to have squared error? To have squared error because error might be positive also, error might be negative also. Fine. But error is error. Neither I want positive error nor I want negative error. Both of them I want to remove. So the way of converting negative number into a positive number is to square it, isn't it? So I take square of the error. So for every pattern, I will calculate this error, that is xki. Okay, xki is input pattern of ith person. OTI is the error for ith person. Okay, target for ith person. Note that OTI for a boy, it will be 1. For a girl, it may be -1. Okay, whatever is the error, it will be squared, it will be summed, and then a parameter, virtual parameter of 1/2, or it is also called as regularization parameter of 1/2 will be added. Why to add this 1/2? You will understand it further. Now we want to minimize the squared error. If I minimize the squared error, actual error will be automatically minimized. Whether it is positive error or negative error, I want to minimize both. That's why I have taken squared error and I am going to minimize it. Fine. Now, a mathematical algorithm to uh, to reduce this error is called as gradient descent. Fine. Error gradient descent. So you first find out error. Okay. Then descent means what? Reduce, reduction, or change. And gradient is rate of change. Fine. You control the rate of change of error. That's why the name gradient error gradient descent. So you calculate error. Okay. So that is squared error. You calculate its gradient. You might have already studied in your differential. How do you calculate gradient? By differentiating a quantity. Okay. So you differentiate squared error. So you will get DSE. With respect to what? With respect to WK. Because I want to have appropriate value of WK. That's why error is differentiated with respect to WK. Now, preliminary or basic of this mathematics you have already studied in 12th standard. You might have located maxima and minima. So how do you locate maxima and minima? How do you find out maxima? You differentiate the expression and equate it. You will get either maxima or minima. Fine. Same thing we are doing here. We are differentiating squared error. Now, when I differentiate squared error, what is differential of a square? What is differential of a square? X square suppose is there. What is differential of x square? It is 2x. Fine. 2x. Now here, that square of the bracket is there. If I take its square, what will happen? It will be 2 into that bracket. So for cancellation of that 2, that 1 by 2 has been added. Otherwise, in your computations, you will have to multiply your differential by 2. So to save those computations, we have added 1 by 2 there. Now what will happen is, after differential, whenever that 2 comes, that 2 will cancel with 1 by 2 and you will get the following term as given there. So as you already know, differential of a summation is summation of differential. So k is equal to 0 to n summation as it is. 2 will cancel there and differential will be, in fact it will be wk xki minus oti. Okay, but for a general term I have written wk xk minus ot, out of which ot is constant. So further differential of wk xk will be xk with respect to wk. Okay, and this again I can write like this. Fine. Wk xk, summation of wk xk minus ot is nothing but o minus ot, again using the basic principles in summation, basic mathematics, o minus ot into xk. So this is nothing but gradient of the squared error with respect to wk. And whenever I write gradient descent algorithm, what I write is wk on the left hand side is new weight, that is equal to, on the right hand side wk is old weight, minus, now suppose I find an error. Okay, I find some error in my work, and if I all of a sudden try to correct that error 100%, what will happen? What will happen? There might be some side effects. Even if you understand that you have some mistake, done some mistake, it should not be that the mistake is corrected very abruptly. Suppose, for example, you are a student and you fail in the examination. Okay, earlier you were not in habit of studies, so you have failed. You were studying 0 hours per day. Now from the next day, you should not start studying 16 hours per day, because that may impact your health. There might be other side effects. Many of you may have your children and you observe that they are committing some mistake, and if you try to brutally tell them to correct the mistake, you already know the younger generations, they will rebound. They will rebound. They will not listen. Forget about following you. They will rebound. Okay. So any mistake which is there, that should not be corrected abruptly in one go. So whatever is the error, some percentage of the error can be corrected in this iteration. Some percentage of error can be corrected in next iteration. And eventually in 10, 15, 20, 100 iterations, the error might be minimized. Okay. So to control this, there is one parameter that is added to the equation, that is eta, that is called learning rate. So wk is equal to the old value, new wk is equal to old value of wk minus learning rate eta multiplied by the gradient of the squared error that is given in the earlier equation. K is equal to 0 to n o minus ot xk. For batch training, we calculate single value of wk, that is equal to wki minus eta into o minus ot into xki. Okay. In case of batch training, what you do is complete error for all patterns is added, and that is provided here in the equation after learning rate. Okay. For stochastic learning, there can be individual, the summation of complete error. This is there for batch learning, and for stochastic learning, batch learning means error for whole batch is considered. Stochastic learning means error for every sample is considered. So O minus OT is a single sample. So error of single sample is there for stochastic learning. Thus, each new weight is computed as the original weight minus the learning rate eta multiplied by the gradient of the squared error. This is called very fundamental gradient descent algorithm. Fine. But obviously, you can imagine the drawback of this algorithm. If your eta is small, then it will take a lot of time to converge. You want to correct yourself. Okay. You want to correct yourself. You will have to make the correction in due time. The correction should not be so late that it is meaningless. Many times you do the corrections, but the time taken for the correction is so large that the correction is meaningless. For example, a first year student, suppose he fails in first semester, and if he wants to correct himself, and if he take 20 semesters to correct, the duration of 5 years or 7 years to correct, it is meaningless. He will have to correct himself in 1 or 2 semester or 3 semesters at the most, so that by the time he reaches final year, he gets some good pointer and he can get some good job. If he takes 10 years to correct, then the correction will be meaningless. Fine. Thus, the learning rate should not be very small. At the same time, learning rate should not be very high also. If the learning rate is very high, what will happen? He will have to work 16 hours a day. It may impact his health. He may lose even his emotional balance, because in the course of that time, he may lose his friends and so on. Okay. So whenever learning rate is too low, it will take a lot of time to learn. If the learning rate is too high, there might be other side effects. In case of neural networks, if the learning rate is too high, it generates oscillations amongst the output. The output is not stable. Okay. This has happened. Even you might have also observed such cases, senior teachers especially. Some students are there, they abruptly try to work hard, and then they lose their emotional balance, they lose their mental balance. Oscillations. These are representation of oscillations, oscillatory response. Or those who have studied EDC, they might be knowing or remembering the principles of oscillator. If there is positive feedback, what happens? Continuously the input increases, and a stage comes at which oscillations start getting generated. Okay. We call it Burke-Hansen criteria of generating oscillations. Fine. So anyway, coming back to our topic. Now what will happen is, if there is an output, I have got only one output node. In the last node, I have got only one output node. So what can I do? I can have +1 for say output class 1, and suppose I have another for class 0, means 0 for class 0. What will happen? The same output node will be forced to class 1 in one iteration, and the same output node will be forced to class 0 or class -1 in another iteration. Okay, the learning of the neural network will not be smooth. Try to imagine, a person is there, you are telling him one pattern now, okay, one example now for one thing, and second example is given for second thing. Okay, he won't be able to learn. How you will have to train him? You will have to train him by giving 4-5 examples of class 1, 4-5 examples of class 2, and then you can keep on repeating, and then you can keep on repeating. Fine, for better learning. Now there is one output node, you give it class 1, it will generate output 1, and for the second pattern it will generate -1. Many times what will happen is, I want only +1 and -1. What I may get is +2 or +3. What I will have to try to do is, I will have to force them to +1 or -1 or +1 or 0. How this should be done? This is done using an additional mathematical function. Okay, I define the earlier neural network transfer function as t, small t, that is equal to k is equal to 0 to n wk xk, and I have a function ft, okay, for which t is input, 1 divided by 1 plus e raised to minus t, that is 1 divided by 1 plus same function. Note that at t is equal to 0, ft is 0.5 exactly at the center, that is representing boundary of the class. At t is equal to infinity, I should have f of t, okay, means the point is very much in class 1. At t is equal to minus infinity, I am going to get f of t is equal to 0. F of t is equal to 0. Okay, so that I get two classes, t is equal to 1 and t is equal to 0. If I want to have t is equal to f of t is equal to +1 and f of t is equal to -1, I will have to do some arithmetic manipulations here. It is very easy, not at all difficult. You can imagine, I will have to in the numerator write 2 or multiply this function by 2, and then I will have to subtract -1 from this. That is going to give me output from +1 to -1, that we call soft signum function. Fine, soft function, which will give me +1 and -1 output. So the rough plot of this function is shown here between 0 to 1. Now this particular function I will have to add at the output. So I am doing that in the next slide. See here, this red block is that nonlinear function. Okay, earlier circuit is our original neuron, say output is given by f of t, where t is equal to k is equal to 0 to n sigma wk xk, 1 divided by 1 plus, in place of e raised to minus t, this bracket is there, and this will be my output. Now whenever I apply gradient descent for this, you can imagine, earlier we have calculated gradient descent of error at the output of summation block. Now I will have to calculate gradient descent at the output of this red block. So I will have to take differential of this also. I will have to take differential of this also. Okay, so the weight updation rule, it is now modified using this. It is given by error 1 by 2 again as usual, 1 divided by, earlier it was sigma wk xk, now it is 1 divided by 1 plus, now O is defined like this. O is defined like this, O minus OT, in place of O You can see the square green black, rectangular green black, it is substituted here, and OT is a constant. Now if I apply gradient descent here, my equation will be like this: WKI is equal to WKI minus learning rate eta multiplied by gradient of the error. So n multiplied by differential of this. Now calculating differential of this is a slightly mathematically complex function, okay, but it is not impossible. Now the advantage, there will be an issue, there might be many functions which can provide me this soft function, okay, between 0 to 1. Why I have selected this function only? This function is a typical function of which differential is calculated from the function itself. You in fact need not differentiate numerically. For other functions you may have to differentiate numerically, but for this particular function 1 divided by 1 plus e raised to minus t, its differential can be expressed in terms of itself. Now you see this red expression here, okay, the differential is represented 1 minus ft, computationally very simple, multiplied by ft minus ot multiplied by xk. Now note here that you are calculating the differential only using value of ft, only by multiplying the things. No additional differential operation is required, and that's why this particular softmax function is very important, okay. Soft thresholding function, not softmax. Soft thresholding function is very important, and gradient descent rule, it takes shape of this equation. Now the problem with this earlier circuit is that the same neuron in the, there was only one neuron in the output layer. The same neuron will be forced to class 1, the same neuron will be forced to class 2, and this will create confusion, okay. So what has been done now is I have added additional neuron to the output layer. So O1 will represent class 1, O2 will represent class 2. O1 will go 1, logical 1, when the pattern belongs to class 1. O2 will go to 0 or minus 1 when the pattern belongs to class 2. Whenever I give pattern corresponding to class 1, I will apply the input here, okay. O2, O1 is supposed to 1, it is belonging to class 1, so O1 should be 1, O2 should be 0. So I will modify all the weights which are in green boxes using gradient descent, such that this output error is reduced, okay. This is forced to 1, and I will apply all the weights in orange boxes. I will change all the weights in orange boxes so that O2 goes to 0, because my first pattern is corresponding to a boy class, say, or it is corresponding to class 1, and that's why O1 should be forced high and O2 should be forced low. Whenever I apply a pattern corresponding to a girl, or say class 2, I will apply the input parameters, and I will force, or I will change the weights such that O1 reduces, it goes to 0, and I force O2 to 1, because O2 is representing girls class. Fine. So this way I can now write the equation using two matrices like this. Now I am using matrix notation. W01, fine, W11, W21, Wn1, first row of matrices, fine. Then W02 is bias weight, then W12, W22, Wn2, all the symbols are written here, fine. And there is matrix 1, x1, x2, 1 correspond to the bias, okay, which will be multiplied to the first element of the row, and the output O1, O2. O1, O2, as I have already described, 1, 0, perceptron yield output O1, 0 as 1, 0, okay, if it is class 1, and it is 0, 1, okay, if it is class 2, fine. So you will have to change these weights by using gradient descent, fine. So this is a two-class classifier. So far we have studied two single layer two-class classifier, but I have told you that even these two uh, layer may not be enough, because so far we have been thinking of classification between the two classes which are separable by a single line. We have seen the example, single line may not be enough. I may need 2 lines or 3 lines or 4 lines. Not only that, in real life application, I may not have only two classes like girl or boy, or yes or no, or true or false. I may have many classes. I may require many classes in the output. Okay. For example, from the facial input, I want to justify, I want to recognize whether the person is happy or sad or irritated. Okay. I may have many feelings. Corresponding to every feeling, I will require one output in the output layer. Note that here, the number of neurons in the output layer are the number of expected classes, fine, and number of inputs in the input layer, they are number of features plus 1. Plus 1 is there for the bias. So for any given neural network, how many neurons are there in the output layer? They are equal to the number of classes, okay, in which I want classification of the input pattern. Fine. If I am recognizing currency note, I may require one neuron for 1 rupee note, second neuron for 2 rupees note, third neuron for 100 rupee note, fourth neuron for 50 rupee note, fifth, sixth neuron for say 500 rupees note, seventh neuron for 200 rupees note, eighth neuron for 2000 rupees note. For every note, I will require one neuron. Fine. And that particular neuron corresponding to that note, there its weight will be forced high, changed to high to achieve high output if features of that particular currency note is applied at the input. Is it clear? Using gradient descent, this is how the training of the neural network proceeds. Okay. Now training of two-class classifier, again I have derived equations here, but in this lecture, as I already told, it is not possible to cover all mathematical equations. I have derived all the mathematical equation for different classes. I won't explain it. Basic principle is same. Now see here, instead of two classes, I have shown m classes, O1, O2, dash 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 OM. Fine. Again, same equation can be used for training all these classes. Okay. Whenever I apply a particular pattern, output corresponding to that pattern will be forced 1, and the weights will be changed accordingly using gradient descent. All other outputs, they will be forced to 0, and their weights will be changed accordingly. So this particular perceptron has got m outputs. The features are n. Fine. Again, gradient descent will be used for training. Now there is training of an m class classifier. Fine. So how to do it? Again, we are going to study only gradient descent, only discuss only gradient descent. But what about the architecture? Architecture will look like this. I have added only hidden layer 1. Only one layer I have added. Okay. Now I was changing the weights with respect to W, isn't it? Output O1, I can calculate error, and I can take differential with respect to W for the output. It is easier. But how do I change weights of middle layer? For changing weights of middle layer, I do not have target output of that particular layer. Are you getting my point? Target output is defined as 1 or 0 or 1 or -1 only for output layer. Target output for middle layers are not defined, they are unknown. In that case, how do I calculate the differential of error with respect to these weights? Note that for this, something called as chain rule of differentiation is used. In simpler words, you need not worry about what is chain rule of differentiation and all that. Simply, you can take error of the output or change in output with respect to change in weight. Okay. And for calculating this change in output and change in weight, you can use earlier weight matrix, earlier 2 iterations of weights. Fine. That can very easily give you the gradient of the error with respect to W. Okay, because you already know for calculating gradient descent what you were requiring, dE or d error, differential of error divided by dW. How will you get differential of error? For calculating differential of error, current error and last error, you will have to take it difference. In the denominator, last weight and the weight before that, and the weight before that, that will give you dW. You have already carried out numerical differentiation. All of you, at least computer students, they must have studied a paper on numerical methods. Even electronic students also might have studied numerical methods, and there you must have studied how to calculate differential. Okay, so you will calculate differential of output error with respect to differential of W, means change in squared error at the output divided by change in squared error of the weight, change in value of the weight. Okay, and these values, they will be used for previous iterations, from previous iterations. Fine. So this way, even if there are large number of hidden layers, there might be hidden layer 2, hidden layer 3, and so on. So every time whenever you change the weights, you will have to take error in the final output divided by error or change in the weights in earlier iteration. So this way you can train even multi-class classifier, multi-layer classifier. This is, in fact, I am showing only one hidden layer. If there are m output classes and if there are large number of hidden layers, the neural network will look like this. This I have already discussed. The last equation is called as chain rule. I can write it for 10 layers also. See now, for simplicity, only 2 hidden layers, but I can have n hidden layers in between. I can have z output classes, and using the same gradient descent equation, I can develop equation for our program changing the weights for a given input pattern and its known pattern, known class. Fine. So this is what is called gradient descent algorithm. There are different algorithms, advanced algorithms available for changing the weights, but they are all derived basically from gradient descent. There is gradient descent with momentum and all that. So I am, for clearing your concepts, I am taking only basic gradient descent, and this particular neural network, this is large number of hidden layers, fine, and large number of outputs. Okay, and this will be trained by gradient descent. Now the issue is why I have given so much time to this network. This is because this is the second stage of deep neural network learning. This is second stage of deep neural network, and this is the actual classifier. Fine. In deep neural network, you have two parts, two stages, I will say. The first stage automatically detect features. A feature vector is prepared. Fine. And that feature vector is applied as input to this x1, x2, xn. This classifier is trained appropriately so that the given input pattern is automatically classified amongst O1, O2, OZ, Z classes. I have shown here 2 or 3 layers, 2, 3 neurons in the output, but let me tell you, the commercially available deep neural networks, they have 300, 400 layers even. And many of them, they have 10,000, 20,000 neurons in the output layer. Okay. And the features at the input, they are also in lakhs. Okay. Even more than lakhs. In many commercial applications, even they are more than lakhs. Fine. So the size of neural network is huge. Deep neural network is huge in size. But then what is the advantage? The advantage is that it automatically detects features. Try to remember my example given by me about students. For a particular student, I have given you height, weight, IQ. But who will give you this height, weight, IQ? You will have to measure them by using separate processes. Height, weight, IQ for every student. But if height, weight, IQ is not known, then you cannot use this neural network. Okay. And that's why deep neural network became more popular. Feature detection in pattern recognition applications. Which features are to use? Okay, how to compute them, their computational complexity, they are very, very difficult to handle issues. And that's why deep neural network, they automatically decide which features to use. They automatically compute the features. They automatically neglect even unnecessary features. Feature cleaning or data cleaning is also many times automatically done. And that's why deep neural network has become very popular. Fine. Now, deep learning using features at multiple levels concept. Now, what is deep learning? When I talk about deep learning, everybody talks about deep learning, but nobody clearly knows what do you mean by deep learning. Somebody says there are more number of layers, that's why it is deep learning. Somebody says there are large number of neurons, that's why it is deep learning. Large neuron agar hai, if a particular person has got very good brain, does it mean that every time he does deep learning, neurons are more? So does it mean that he is learning deep every time? No. A person with large number of neurons can also shallow learn. Fine. So deep learning is not always related to large number of neurons. It is quite possible that in less efforts, the person with good brain may be able to learn in depth. That is fine. But large number of neurons always do not correspond to deep learning. In general, when we talk about learning in depth, means what? We say that I have only learned it once, I have not learned in depth, or I have read it once. When you read it 10 times, you understand 10 different things from that material. You come out with 10 different interpretations. You come out with 10 different meanings. In short, in the language of pattern recognition or artificial intelligence, you come out with large number of different features. Okay, it means you have extracted huge amount of information or knowledge from the available data. And learning in depth or deep learning means you will extract large number of features, you will extract huge amount of knowledge from the available data, because you already know if data is there, all data is not information, and all information is not knowledge. All information is not knowledge. Then what is the difference? Information lies in the relation between the data elements. Data itself might not be information, but the information lies in relation between the data elements. Fine. Then what is knowledge? Is knowledge information? Again, knowledge is not all information. Knowledge is the contextual interpretation of the information. So these three are different levels. There is data, there is information, okay, and then there is knowledge. For example, in a particular class, a particular student or list of marks is given. That is data. That is data. You observe the marks, okay, try to find out its average. The average is suppose 80. The average is suppose 80. So the class performance of the class is very good. This is information. Performance of the class is very good is information. Fine. And then what is knowledge? The knowledge is might be, I am not saying is, the knowledge might be the question paper was cheap. That's why average is 85. You might be evaluating your papers, and suppose in some subject average is 90. Average of the whole class is 90. What does it mean? It means question paper might be of poor quality. Okay. In case of online days, online examinations, result was 100%. Does it mean that the quality of those pass outs were much better than offline examinations? Certainly not. They got more marks, that is fine. That is what is all about deep learning. In case of deep learning, the algorithm and the neural network, it has got large number of neurons. It is capable of extracting different features. There are large number of convolutional filters to extract information, to extract features. Large number of features are extracted at various layers, at various levels. All those features are concatenated. Okay, less meaningful features are left out, they are dropped. You might have heard the terminologies ReLU, isn't it? You might have heard the terminologies like max pooling. Both of them, they remove unnecessary features, meaningless features, and preserve only important features. Okay, this is just like you learn something in deep and then you understand that this is not meaningful, this is not important, and you drop that material. Whatever is most important, that you learn and preserve. Fine. That is what is deep learning. So thus the deep learning algorithm directly accepts a noisy, distorted, even incomplete input pattern. On its own, it directly detects unknown multiple numerical features automatically, and then classifies the input pattern for a real life application. So can I represent it like this? See here, how was conventional learning neural network or other classifier? Input pattern was given, an engineer or a user, he was pre-processing the input pattern, input data, denoising, feature identification was done, feature computation was done, insignificant features were rejected, and those selected features were given to either neural network, fuzzy logic, statistical learning like regression, interpolation, and so on, Gaussian regression classifier, and so on. So this is what is conventional learning classifier. Okay, this may even have other machine learning algorithms in conventional learning. What is there in deep learning? In deep learning, you give only input pattern smiley. You do not give any pre-processing, no denoising, no feature identification, computation, and nothing. There is a block called as autoencoder. What does that autoencoder do? That autoencoder, it extracts multi-level unknown feature identification. It identifies the feature. It computes the feature. It removes unnecessary features using principles like ReLU and max pooling, using multiple convolutional layers. Fine. And those features are applied to fully connected feed-forward multi-layer multi-class neural network classifier. So far, we have already studied fully connected feed-forward multi-layer multi-class neural network classifier. Fine. Now we will try to study this first block. I completed second block first because many of us have studied neural networks and we have got some understanding of the issues. Same concepts are used in autoencoder also. Okay, and that's why we are we have studied second block first, and first block now we will study. I'll take a 5 minutes break. Will you please excuse me for that?
Sure, sir.
Sure,
Huh?
sir.
We'll take 5 minutes break and later on we will continue.
Okay, sir.
Yes, sir.
So yeah, I am ready to get back.
Sir, you can continue, please.
Okay. So these two diagrams, they can explain you the philosophy of the, or difference between philosophy of the conventional classifiers and deep learning classifiers. So block diagram of deep learning network, it will be like this: input pattern, autoencoder. Now when you talk about autoencoder, there can be, I mean, two types of autoencoders. The types we'll study further, and then finally it will be fully connected feed forward neural network classifier. Now when we talk about deep neural network, there are some basic concepts, as I told you some name. First thing is convolution. I hope convolution you people might have already studied. Yes,
Yes, sir.
2D
Yes, yes.
convolution you have already studied. So you take
Yes.
a filter
Yes.
mask. You take a filter mask, might be 3 by 3 size, 4 by 4 size, 5 by 5 size. Okay. You locate its center or reference point as shown here for F2. Okay. And that F2, what you do is you time invert it in both the direction. The process of time inversion is given here. And after time inversion, you place it over F1. The last matrix given, big matrix given, is F1. F1 is our actual pattern. Now this particular convolution matrix, a time inverted convolution matrix, you first slide along x direction, and after the first row is over, you take it to the next row. Okay. So this is how you implement conventional convolution. And at every position of the mask, you multiply the overlapping elements. Like here I have given one example here. The matrix F2 after time inversion is 1 to 9, 8, 5, 2, 7, 3, 1. Okay, this green marked matrix, and this is now getting multiplied with this first element 583, 169, and 623. So if you multiply the corresponding elements means 1 1 multiplied by 1 1, 1 2 multiplied by 1 2, and so on, 3 3 matrix element will be multiplied with 3 3. And if you add all those multiplications, you will get 155, and that 155 will be placed at the central position of 5. 5 is the central position. Okay. And when it comes to the feature matrix, it is central position is 6. So at this 6 position of 6, you can see that in F1 convolution F2 there is 155. It is quite obvious that with 3 by 3 convolution matrix, you cannot reach the border position. That's why all the border position, they are marked X. Fine. And this filter matrix, it should not exceed or go out of the feature pattern matrix or input pattern matrix F1. Fine. If you want to exceed that, then you will have to do zero padding. Fine. So this is what is convolution. Now there are two similar operations. One is convolution, another is correlation. When it comes to correlation, correlation is used for finding out similarity. Okay. But note that features lie in dissimilarity. Features lie in dissimilarity. And dissimilarity means high frequency components. The changes in the signal, changes in the input pattern. So we want features, and that's why we use convolution and we do not use correlation. Right? So this convolutional matrix, wherever convolutional values are high, those high values, those are supposed to represent features of the input pattern. Fine. In case of deep neural network, at one level, you can have 4, 5, 6, 10 such matrices. and you can convolve the input pattern by using those all 10 convolutional filters. You can get 10 results of convolution. You can get 10 results of convolution. So the data will be huge. Now, if the data is huge, what you will have to do, obviously, you will have to remove unnecessary data. Now, when the convolution result is negative, it is believed that features are not there. And it has been mathematically proven also, the features are not there. So what is done is, all negative values are removed from this convolution. I am showing red numbers in this slide. The result of convolutional might be negative also. If the filter has got negative coefficient, input pattern usually doesn't have negative features, as far as image features or video features are concerned. You already know images and videos, they have numbers between 0 to 255, but there might be other uh, biomedical signals and some other patterns in which you may have negative numbers. So if the result of convolution comes negative, that is not considered as important feature. While high positive values of convolution, they are considered as positive features. Fine. So all negative values of convolution, they are replaced by zero. And this is similar to something called as rectification, half wave rectification in electronics engineering. Okay, in case of half wave rectification, you already know it processes all positive halves or values greater than 0, they are maintained as they are, and all the negative values, they are replaced by 0. Negative halves are suppressed, and that's why it is called as rectification. Negative halves are rectified. So after convolution, you apply a phenomenon which is called as ReLU. So transfer function of a typical ReLU is like this. See here, if the input is negative, output on y-axis will be 0. Fine. On the other hand, if the input is positive, output is equal to input. That is what is half wave rectification. And obviously the slope of this oblique line will be equal to 1. dfi by di is equal to 1, because output is equal to input. Okay, this block is implemented by a mathematical function called as rectifying linear unit, and you can very simply implement it. You will read the value from the convolution one by one. Read the value from the convolution. If it is less than or equal to 0, output is equal to 0. If it is greater than 0, then output is equal to that particular value itself. Fine. So you will now get, after rectifying linear unit, all positive values of convolution, and wherever zeros and negative values of convolution were there, they all will be replaced by zeros. Fine. So this is called as rectifying linear unit. And at the output, you have one new block called as a max pooling operator. Now this max pooling operator, what it does is, it takes small neighborhoods, might be 2 by 2 or 3 by 3 or 4 by 4, and it's find out maximum of all those values. Now what this will achieve? When I talk about features, I am interested in prominent features. Less prominent features are not interesting to me. So when I get maximum value of communication, I can say that it is the most important feature, and less values of communication, though they are positive, they may not be important features. So I will like to avoid them. So what I will do is, I will select a 4 by 4 matrix. And out of those 4 by 4 matrix, 4 by 4 matrix means total 16 elements. And out of those 16 elements, I will have only one maximum value. So I have achieved data compression here. Note that due to large number of filters, result of convolution was huge. It was containing large numbers in large numbers. So data has expanded. What rectifying linear unit has done? It has removed negative data. And what this max pooling operator will do is, out of 16 numbers, it will select only one number. Means what? It is achieving data compression. Okay, so convolution detect features, rectifying linear unit removes negative features, non-important rather than non-important, unnecessary numbers. Rectifying linear unit removes. Max pooling unit further removes non-significant features. Rectifying linear unit will remove non-features and max pooling operator will remove non-important features. They are features but not very important. I am taking only maximum of 4 by 4 matrix or 2 by 2 matrix. So instead of 4 elements for 2 by 2, it will have only one number. If you select 4 by 4 max pooling this thing neighborhood, then you will have for 16 numbers only one number. So this will achieve data compression. Okay, so contents of a single convolutional neural network has got these three objects. Convolutional layer is there, rectifying linear unit is there, max pooling operator is there. This is in one convolutional neural network layer. If there are 100 such layers, this block diagram will be repeated 100 times. Note that this block diagram will be repeated 100 times. Okay, and what is the intention of every such layer? To take input from the previous layer or input pattern to implement convolution. After convolution, removing negative values by using rectifying linear unit, and then removing even less positive values or lower positive values, and to select only highest positive values that will represent important features. Okay, and that is what the features from that layer will do. In the next layer, again you will have large number of convolutional features. All these features will be applied to again large number of convolutional features. There will be again convolution, again rectifying unit, again max pooling operator. If there are 100 layers, there will be 100 convolutional filters, convolutional operations. There will be 100 rectifying linear units. There will be 100 max pooling operators, and so on. And that too only for one convolutional filter. Okay, so this is how features are detected in convolutional neural network or during the first layer of the deep neural network. All the features from all the convolutional filters, they are finally concatenated to form a final feature vector. Fine. Now this example of autoencoder, I have already told you that the feature detection is done by autoencoder. Now this autoencoder, as I told you, it detects features. For implementing it, you have two methodologies, two options rather, not methodologies, two options. The first method is feed forward autoencoder. Now what does this autoencoder do? As the name indicates, when we encode something, what does it mean? What does it mean? You have studied in digital electronics also, you have studied encoder. You have studied 16 into 1. Okay, or encoder, when it comes to encoder, 16 is to 4 encoder. What does it mean? It means 16 inputs were converted to 4 outputs, and in some way the 4 outputs were expected to represent properties of all 16 inputs, or in other words, you were encoding 16 inputs into 4 outputs. Okay, or in other words, the encoder was detecting features of important features of 16 inputs. That's why the name autoencoder means encoder there in digital electronics. I hope you remember encoder, decoder, then multiplexer, demultiplexer, and so on. So what does the encoder do? It takes input, it detects features. Okay, so that is function of autoencoder. Now in this given diagram, conceptually, L1, L2 and L3, they are representing encoder. Fine. And note that size of L2 is smaller than L1, size of L3 is smaller than L2. So obviously If this is a feed forward neural network, L1, L2, L3, they are like feed forward layers. At the output of L3, you will have less number of outputs. Number of input f of xy was large. So obviously, if I am training this network of autoencoder properly, okay, output of L3 is representing f of x comma y, and it is smaller in size. What does it mean? It means, at least logically, output of L3 will have all important features of input. Non-important features, they will be automatically removed. Why? Because input was huge in size, output of L3 is small in size. But how do I get this small size of L3 very correctly? In other words, how do I get correct features at the output of L3? For that, I will have to do iterative procedure like neural network. How do I do that? At the output of L3, I connect another layer L4, which is same as L2. At the output of L4, I again connect another layer, which is same as L1. And output of L5 will give me reconstructed f of x comma y. I call that f cap f of x comma y. And I expect that I will change the weights of these layers, neural network layers, such that the difference between f of x comma y and f cap x comma y is minimum. Or I will call that loss function between f of x comma y and f cap x comma y is close to 0 or minimum possible. If it is minimum possible within accepted limit, I can believe that output of L3 is having all important features of f of x comma y. Okay, because using this output of L3, I am reconstructing f cap xy, which is approximately equal to f of x comma y. What does it mean? It means all important features of f of x comma y, they are already existing at the output of L3. Or in other words, non-important features of f of x comma y has been removed. And that's why even if I am dropping non-important features, I am approximately constructing the same signal f cap x comma y, of which error with f of x comma y is very small. Okay. So if I carry out this training procedure, if I carry out this neural network training, and how will I calculate the error? Error will be obviously f cap x comma y minus f of x comma y. And then of course that squared error, this, that, okay, gradient descent, everything is applicable. Weights will be modified and the training will stop when the difference between f of x comma y and f cap x comma y is minimum. Fine. And whenever this training is complete, what I will do is I will remove decoder from here. This orange block portion decoder I will remove, and this feature, that is output of L3, I will connect at the input of feed forward neural network, which we have already studied, and that will give me the classification. Fine. I hope the basic concept of autoencoder and autodecoder is clear to you. So this autoencoder is nothing but feature detector, automatic feature detector. In the input, I am giving only f of x comma y. I am not giving the features x1, x2, x3 like we were doing in neural networks, conventional neural networks. Fine. There can be another. This is called as feed forward autoencoder because the neural network layers which I used, they were layers of neurons. Now there is something called as convolutional autoencoder. Instead of feed forward neural network, I have now convolutional layers, and every convolutional layer has got the three blocks I described earlier. It will be convolution, there will be ReLU, there will be max pooling. Okay. Let us assume that capital N is size of input f of x comma y. Means if n is 100 by 100, I consider n is equal to 100. Fine. Convolutional filter size is suppose small n. That is size of f2 is small n. Let us assume that it is 5 by 5. Zero padding is used of 2 rows and 2 columns. Note that whenever convolutional filter is 5 by 5 or size is 5, zero padding required is 5 by 2. It is rounded off to lower value, that is 2, that is rows and columns, so that you can have all rows, all columns from the input pattern. Okay, no border effect is there. Fine. Then z is equal to 2, that is zero padding is equal to 2. In fact, here it should be this z is on one side. Total zero padding is 4. 2 rows on left and 2 rows on right. Fine. Similarly, when I displace this filter over the input signal in convolutional operations as a convention, I displace the filter matrix by 1. But you know, this will generate lot of data. So to avoid some data, or to sample the actual convolution, what we do is, rather than displacing the matrix by one column at a time, we can displace it by 2 columns or 3 columns, similarly by 2 rows or 3 rows, and that is called as stride. Fine. Stride is nothing but, if you find out the meaning, dictionary meaning of stride, it means jump. It means jump. So you can make the convolutional filter jump by 2 positions, 3 positions, and so on. So if you apply this formula, in fact, this formula is not very correct. This +1 is not here. This +1, in fact, it is capital N minus small n plus z. This +1 is not here. It is -1 outside. You can search this formula on the internet. You will get it easily. The actual formula is like, now this has been converted into a diagram. So I am unable to edit it. So it is C is equal to, the formula is like this: N, capital N minus small n plus Z, where Z is zero padding on both the sides, divided by S. This is one factor, and this complete bracket -1. This is your actual size of convolutional result. Okay. So somehow for these parameters, the convolutional result may come. You will have to calculate it by applying correct formula. This calculation are also accordingly wrong. So please don't go on this formula. Just remember that some such kind of formula is available for calculation of size of the convolutional result. Now there can be convolutional encoder, autoencoder, decoder also. So I will directly go to its diagram. See here. This is the architecture of deep learning. Oh, this presentation doesn't have a direct diagram of convolutional neural network like this, but you can imagine in every layer, in every convolutional layer, you have such dotted box. This one dotted box is one layer of deep neural network. Okay. Now for one layer, I am showing how many filters here? 6 filters. You see here, there are 6 convolutional filters, 3 plus 3, 6. In the red dotted box, you see there are 6 convolutional filters. Now these 6 convolutional filters, I am making the filter jump by 2. When the filter jumps by 2, the alternate sample is dropped. If the alternate sample is dropped, what will be the size of the convolutional result? Obviously, the size will be n by 2 by n by 2. There are 6 filters. For every filter, there is one n by 2, 1 by n by 2 by n by 2 result. I will get 6 output convolutional result as shown. 6 convolutional result will be applied by 6 ReLUs. There are 6 ReLUs shown. There is max pooling. Max pooling doesn't change the size, But then whenever there is stride of equal to 2, that S dash is equal to 2 is nothing but stride of max pool. So that max pool will also again divide each input by 2. So it will be n by 4 by n by 4. So corresponding to 6 filters, I will get 6 n by 4 by 6 n by 4 by n by 4, 6 matrices in layer 1. Now note that in layer 2, all these 6 matrices, they will be again applied to more than one filters. Now if I consider that there are again 6 filters in the CNN2 layer, purple block, what will happen? Can you imagine? All same parameters are there. First layer has generated 6 output. Okay, size is 1/4. But in CNN2, if there are again 6 filters, what will happen? It will generate 36 output. 6 into 6, 36. If there is third orange layer, it will be 36 multiplied by 6. Because in every layer, there are 6 filters. Fine. So it will generate 36 by 6 outputs. Fine. If there is one more layer, then 36 multiplied by 6 multiplied by again 6, 36 square. Okay. And every time, if stride is 2, it will be dividing the input by 4. So purple layer will give you n by 16 multiplied by n by 16. Orange will give you n by 16 multiplied by n by 16, and so on. Finally, output of all convolutional layers, final convolutional layer, it will be concatenated like x by 1 feature vector, and it will be applied to a 3-layer fully connected feed-forward perceptron classifier, which we have already studied earlier. And the output layer of the feed-forward perceptron classifier, it will give you the actual class of the input pattern, that is image n by n. Fine. So this is what is the complete architecture of a deep learning network. But note that when I try about training of all these layers, it is computationally very expensive. And read these orange lines. Many industries and professional bodies have already trained CNNs for different applications. You can take one such trained network and you can readily use their weights. Fine. Their trained size of network and weights are available for CNN applications. Those weights can be readily adapted and you can change and train fully connected network only. This black layer itself you can change by maintaining the input layers. Fine. Even you can, for a few iterations, you can even change these CNN layers also, weights of CNN layers also. So this process of taking the already trained weights from the already existing networks, that is called as transfer learning. Whoever are saying that they are working on deep learning, note that 99.99% people, they are using this transfer learning, because training of convolutional neural networks is very computationally extensive and expensive too. In India, we mostly do the same transfer learning. We tried to train the network from scratch. Means if you do not take their trained networks, then you will have to train it from zero, right from starting by taking random nets. We tried to do that, and on our machine, i7 machine with 128 GB RAM and 4000 GPU NVIDIA cores, we have got a very powerful high performance GPU computing machine. And for our network of football detection, we trained the network for 7 days, and after that roughly 30% task was completed. You can imagine how much it will require for full training. The computer was running day and night 24 hours, and after 7 days only 30% was, roughly 30% was completed. And what was the capacity of the machine? 4000 NVIDIA GPU cores. That's why in many institutes it may not be possible to train a network from scratch. So what you can obviously do is use transfer learning. Now training CNN classifier is again done using either gradient descent or gradient descent with momentum to increase the speed, because I have already told you it is very slow. So somehow you have to use the fast networks, fast learning algorithms. So people use training with momentum, but still gradient descent is the only algorithm mostly used. So that's all about deep learning. And scope of research in deep learning is this: you can have wavelet based design of convolution filters. How many filters should be there to classify a database or for a specific application? That is area of research. Different functions other than ReLU and max pooling are again area of research. How to find the filters, whether to have 5 convolutional filters or 6 convolution filters, nobody knows. Then convolutional mask, number of convolutional filters of appropriate sizes. Then feedback CNN, fast tuning of CNN, customized design of CNN architectures, they are all areas of research. But note that all of them require very fast computing system. And I expect that if you want to complete the training by 5-6 days, in 5-6 days, 24 hours running, 16,000 GPU cores may be required with memory more than 128 GBs. So some of the commercially available networks are LeNet, LXNet, VGGNet, GoogleNet, ResNet. At our institute, we have used VGGNet and YOLO V3, V4, V5 for 2 applications, that is detection of football. One of my PhD students, Paresh Kamble, he has worked on uh, football videos, detection of football in the during the game, okay, and detecting whether the football is inside the game, outside the game, and detecting position of the football. And then we have carried out one consultancy project on detection of speed of vehicle and number plate reading. So for that we have used YOLO V3, V4, and V5. So I think with this, how much is the time? It is already 9:40. So I have already overrun. So thanks for patient listening. And now what I will do is I will play only 2 videos in 2 minutes, and let me see whether you can see those videos. I will simply show you the videos running, and you please tell me whether you are able to see the videos. Okay, so I am playing. Are you able to see the video?
Yes, sir.
Yes, sir.
So you can see the detected car and its speed. Fine. So for every vehicle, it is taking the photograph of the vehicle and displaying in red characters its speed on the photograph. Fine. So this was done using YOLO. Fine. Then there might be another video also. Here the camera resolution was less. That's why you can see that the photographs are little bit blurred. Fine. Further, we have taken better capacity resolution camera, and we were even able to read the number plates of this video, detect number plate and read the number plate. That videos are not right now with me. Those whoever are interested, they can contact me, and later on I can show you those things. Now I can show you the videos. See here at the center it is written ball out of frame, ball occluded by the player, and whenever the ball comes inside, you will find that it is detecting the ball positions by white dots. See here, the ball is moving, so trajectory of the ball it is showing. Okay, so this white position is overlapped actually by green position. You see, green position means what? It is ground truth. You will find that there are some green dots during which my algorithm could not detect the positions. Fine. But when the green is not visible, it means it is exactly overlapping the ground truth ball position. So this was our initial level work. So it is not very accurate. but in many videos at final stages, it was very accurate. See, now ball is not in the field. So at the center, it is writing ball out of frame. Now, as soon as the ball comes inside, it will start automatically. The algorithm is using deep learning. It is continuously watching for the ball. Now, see, flares have come. See, as soon as the ball come, initially it could not detect because the algorithm takes some time for detecting. This computer is not very fast enough on which we run the algorithm. But as the play moves on, the position of the ball can be detected. Fine. And even it is annotating the current state of the game, ball out of frame. It will show whenever player holds a ball or player hides a ball, it will write player ball occluded by a player. So this way you can implement real life applications using deep learning. So I think at this time I should not take much of your time. I have already taken, I think, 2.5 hours. We started at around, I think, 7:15. So game is hold up. So see, it is locating the tentative ball position. Now complete grid is there, means it missed the ball position and it is searching in all the areas, possible position of the ball. And as soon as the ball comes inside the frame, it will start tracking it. Observe it, observe it. See, it has come inside, so it has tried to track it, and again it has gone out of the frame. So this way continuously it can track position of the ball. Even when it will track, now the situation is not here, but whenever that ball enters into the goal post, whenever the ball enters into the goal post, it will declare at the center that the ball is in goal post. Fine. So let us stop here for today. That's all from my side. Thanks for patient listening at this odd time. Those whoever are listening, because most of the times in online listening, only camera is listening and the audience is absconding. So anyway, that's all from my side.
Thank you, sir. Participants, any queries? Okay. Nikita is saying no. Okay, fine. So I would request Swati to propose a vote of thanks.
Okay, thank you, ma'am. Sir, please stop your presentation.
Yeah, yeah, yeah. I hope it has stopped.
Uh, yes, sir. Yes. Thank you, ma'am. On the behalf of Information Technology, I would like to thank Dr. Burchandri, sir. Sir, your lecture will definitely help us to understand the basics of learning, multi-class classifier, mathematical calculations for classifiers, deep learning, a clear difference between the deep learning and the conventional learning. Then many more topics are there, convolution neural networks, and then encoder decoder. Sir, we expect some more interaction with you in future. Thanks a lot. Thank you very much, sir.
Thank you. Thanks for invitation.
So, good night, sir.
Good night. Good night. I'm dropping out.
Thank you. Good night, participants. Thank you. You can leave now.